To understand the limits of data processing, we have to look at the mechanics of the most common bottleneck, matrix multiplication. The goal is to take two input grids of numbers, matrix A and matrix B, and multiply them together to generate a result, matrix C. This diagram shows the classical rule for this operation. To calculate a single value inside matrix C, we isolate a specific row from matrix A and pair it with a corresponding column from matrix B to compute their dot product. We multiply the first items together, 1 times 5, and add that to the product of the second items, 2 times 7. The resulting integer, 19, populates the first coordinate of our result matrix. To find the next coordinate, we keep the first row of matrix A, but shift to the second column of matrix B. 1 times 6 plus 2 times 8 yields 22. Moving to the bottom row of our result matrix requires us to drop down to the second row of matrix A, multiplying it against the first column of B to reach 43. Finally, the second row against the second column gives us 50. This element-by-element traversal is the foundational baseline for matrix operations. It is logically consistent, but this specific mechanic leads to a significant problem as matrices grow in size. Translating this mathematical process into working software reveals why the classical method is so computationally expensive. Here is the algorithmic structure for an n-by-n matrix. To navigate the rows, the columns, and perform the internal dot product math, the algorithm requires 3 nested loops. Because the execution time of each of these loops scales with n, the asymptotic time complexity of this algorithm is formally defined as O of n cubed. We can see the weight of this scaling by testing a matrix size of 1000 by 1000. Substituting 1000 into our cubic constraint results in 1 billion individual operations to generate the output. For modern data centers, a billion operations for a relatively small matrix is a high cost. In fields like deep learning, where matrices often have millions of rows, cubic scaling makes the classical algorithm effectively unusable. O of n cubed creates a ceiling for how large a matrix computation can practically be. To scale further, we need an algorithmic paradigm that avoids this 3-loop structure. One common way to optimize algorithms is divide and conquer, splitting a large problem into smaller identical subproblems. This diagram shows the partitioning process. Instead of working with individual integers, we divide the entire matrix into 4 uniform quadrants. These quadrants are now treated as discrete block matrices, A11, A12, A21, and A22. We can now define the math of the final result matrix using these blocks. To find the top left quadrant of our result, we multiply the first blocks of A and B, then add that to the product of the next corresponding blocks. This same logic applies to the other 3 quadrants of the result matrix, giving us a complete set of block equations. If we count the multiplication terms across these 4 equations, we see that the algorithm must perform 8 separate matrix multiplications. This means that by dividing the matrix into quadrants, we have forced the algorithm to branch into 8 separate recursive paths. To see if this actually helps with efficiency, we have to look at the recurrence relation that represents this behavior. Since the algorithm makes 8 recursive calls, each processing a matrix half the size of the original, the core of our relation is written as 8 times t of n over 2. We add an O of n squared term to account for the work required to add those submatrices back together once the multiplications are finished. We solve this using the master theorem to find the final complexity bound. The theorem focuses on 2 values, the branching factor, a, which is 8, and the division factor, b, which is 2. The theorem tells us to evaluate the logarithm base 2 of 8. The result of that calculation is 3. When we map that back into big O notation, we get theta of n cubed. This result reveals why a standard divide and conquer approach fails to improve performance. Although we have partitioned the data, the 8 recursive calls maintain the exact same computational density as the classical method. In 1969, Volker Strassen realized that breaking the n-cubed barrier was impossible as long as the algorithm relied on 8 recursive calls. Strassen discovered a way to compute the same results using only 7 recursive multiplications. Reducing multiplications by just 1 changes the core recurrence relation. Reapplying the master theorem, our branching factor is now 7. Because 7 is not a power of 2, the logarithm is no longer an integer. Log base 2 of 7 is approximately 2.807. This gives Strassen's algorithm a time complexity of O of n to the power of 2.807. By reducing the recursive branching factor, Strassen changed the scaling behavior of the operation, allowing the algorithm to bypass the O of n cubed requirement. It might seem like removing 1 multiplication out of 8 is a minor change, but because the algorithm is recursive, that saving is compounded. At the first recursion level, the difference is just 1 operation, 7 versus 8. At level 2, branches multiply, 64 nodes classically, against Strassen's 49. By level 4, the classical model requires over 4,000 operations, while Strassen's needs only 2,400. There is a trade-off for this efficiency. Strassen's algorithm is more complex and requires more matrix additions, which creates a higher overhead for each step. This overhead makes the classical method faster for small matrices. However, as n grows, Strassen's superior scaling becomes much more efficient. Subqubit complexity is essential for modern large-scale computing, particularly in scientific modeling and neural network training. Strassen's breakthrough demonstrated that matrix multiplication efficiency is determined by the number of recursive branches. In the next lesson, we will derive the specific, unconventional equations used to reduce those branches from 8 down to 7.